In critical care, tissue oxygenation, ventilation, and acid-base status are the primary indicators of a patient's physiological status. When these variables shift, the window for effective clinical intervention is incredibly narrow. Historically, obtaining this data required sending blood samples away to centralized laboratories. Technicians operated complex benchtop equipment, creating turnaround delays of 15 minutes or more while the patient's condition deteriorated. Today, point-of-care testing reduces that wait to between 1 and 5 minutes. Modern handheld analyzers require only 95 microliters of blood, about 2 drops, and process the sample directly at the patient's bedside. By moving the laboratory to the bedside, these devices eliminate therapeutic delays. Rapid blood gas analysis provides the immediate clarity required to target treatment plans without losing critical time. This immediate digital output gives physicians 3 primary measurements: the blood's pH, the partial pressure of carbon dioxide, and the partial pressure of oxygen. But translating a single drop of whole blood into an exact map of cellular respiration requires bridging biology and electronics. Behind the digital readout lies a highly orchestrated sequence of electrochemical translations. Inside the cartridge, the machine passes the blood sample over 3 specific biosensors. For clinicians to properly interpret this data and rely on its accuracy, they need to understand the exact electrochemistry occurring inside the cartridge. We begin with blood pH, which is clinically defined as the negative logarithm of the hydrogen ion concentration present in the blood. The analyzer uses a SANS electrode with a measuring electrode behind a glass membrane. As blood passes, the hydrogen ion gradient alters its voltage. The machine compares this against a stable reference electrode. This electrical delta is then displayed as the sample's numerical pH. Ultimately, the SANS electrode measures blood acidity by converting a purely chemical gradient into a precise electrical differential. Measuring the partial pressure of carbon dioxide relies on a direct modification of this same concept, using a tool known as the Severinghaus electrode. The measuring electrode sits in a bicarbonate solution behind a highly selective plastic barrier. It actively blocks water and external ions, but allows carbon dioxide to slip through. Inside, CO2 forms carbonic acid, which immediately dissociates into hydrogen ions, dropping the internal pH. By measuring this localized, internally generated pH change, the machine gains a highly accurate proxy for the patient's arterial carbon dioxide levels, directly linking their ventilation capacity to their blood acidity. Determining oxygen uptake requires abandoning pH measurement entirely in favor of reduction-oxidation chemistry. The Clark electrode features a platinum cathode and a silver chloride anode. A 0.7-volt potential is applied. As oxygen diffuses through the membrane, it's reduced at the platinum surface, drawing 4 electrons per molecule. Simultaneously, the anode oxidizes, releasing electrons to complete the circuit. The total electrical current produced by these paired reduction and oxidation reactions is strictly and linearly proportional to the partial pressure of oxygen present in the sample. The Clark electrode turns molecular oxygen diffusion into a quantifiable electric current, yielding the patient's arterial oxygen status. With the raw data secured by the hardware biosensors, the software layer takes over. The analyzer combines these direct measurements of pH, carbon dioxide, and oxygen, applying mathematical formulas to derive complex metabolic states. Bicarbonate is calculated by plugging the measured pH and carbon dioxide values into the Henderson-Hasselbalch equation. This chart illustrates the anion gap formula. By adding sodium and potassium, then subtracting chloride and bicarbonate, the resulting gap reveals the presence of unmeasured anions. Calculating this gap is essential for classifying cases of metabolic acidosis. It allows clinicians to differentiate between internal pathologies, like diabetic ketoacidosis, and external toxic ingestions. The analyzer can also calculate the osmolar gap, providing a screening test for unmeasured osmotically active toxins like ethylene glycol or methanol. The diagnostic power of the blood gas analyzer lies in this mathematical synthesis, giving clinicians the data required to manage complex fluid and electrolyte imbalances. But the immense precision of the internal electrodes becomes irrelevant if the physical sample is compromised prior to analysis. Arterial sampling remains the gold standard for measuring oxygen levels. However, venous sampling is often adequate for assessing pH and carbon dioxide in conditions like COPD or diabetic ketoacidosis, sparing the patient the pain of an arterial puncture. Regardless of the source, sample collection faces a strict anaerobic constraint. Exposure to room air, which has an oxygen pressure of roughly 155 millimeters of mercury and near zero carbon dioxide, will immediately skew the native gas pressures of the blood sample. Syringes must also use lyophilized or dry heparin. Liquid heparin introduces atmospheric gases into the syringe and creates a dilutional effect that artificially raises the measured carbon dioxide. Rigorous physical handling is a mandatory prerequisite. Without perfect anaerobic collection, the internal electrochemical translation outputs critically flawed data. Because point-of-care testing decentralizes analysis away from the controlled environment of a central lab, traditional intermittent liquid quality control is no longer sufficient. Traditional manual quality control tests may only occur every few hours or even days. This time gap allows transient analytical errors, like microclots or microbubbles interfering with the electrodes, to go completely undetected. This graph shows the timeline of quality control checks. Unlike the massive time gaps in traditional testing, next-generation intelligent quality management, or IQM2, executes continuous checks every 2 minutes, providing automated pattern recognition directly at the electrode level. By rapidly detecting these physical interferences, the system instantly corrects errors before they propagate, maintaining 6 sigma precision and preventing the reporting of erroneous life and death data. The modern blood gas analyzer functions entirely through the synchronization of electrode-level electrochemistry, microfluidic handling, and algorithmic processing. By understanding the physics of the sensors and the rigor of the quality control protocols, clinicians can confidently turn a drop of blood into immediate, life-saving clarity.